Next, we'll take a look at what's called the 68, 95, 99.7 rule. This is a way to approximate the area under a certain part of the normal curve. A little later on, we're going to learn to find the exact values without as much estimation, either using a z-table or our calculator. But for now, just to get an idea of how this works, we're going to look at this rule, which helps us to estimate. So this rule says that 68% of the data falls within one standard deviation of the mean, approximately. And about 95% of the data falls within 2 standard deviations of the mean, and about 99.7% of the data falls within 3 standard deviations of the mean. That's where this gets its name, the 68, 95, 99.7 rule. You might also see it referred to in other locations as the empirical rule. Let's take a look at how we would use this rule. So, let's say that the distribution of batting averages in Major League Baseball was approximately normal with a mean of 0.261 and a standard deviation of 0.034. First, we'll draw a sketch of the normal density curve. Recall that this curve is bell-shaped, it's symmetrical, unimodal. Right in the middle is the mean, or mu, and then as we go to the left and to the right, we'll go out 3 standard deviations total, so 1, 2, and 3 in the positive direction, and 1, 2, and 3 in the negative direction. They told us that the mean was 0.261, and the standard deviation was 0.034. So we're going to add 0.034 to 0.261 3 times to get each of the new standard deviation values, and then we're also going to subtract it as well. That will give us 0.295 when we add the standard deviation once, and it will give us 0.329 when we add it a second time, and 0.363 when we add it a third time. In the negative direction, when we subtract once, we get 0.227. Subtract the standard deviation again, we get 0.193. And subtract one more time, we get 0.159. The next 2 parts of the question are asking us to find specific percent values. So it's helpful to use our 68, 95, 99.7 rule to be able to label each of these little sections of the normal curve. If 68% of the data falls within 1 standard deviation, and if you go out 1 standard deviation to the left and 1 standard deviation to the right, half of 68 is 34, so that means 34% of the data is between the mean and positive 1 standard deviation above, and 34% of the data is 1 standard deviation to the left of the mean. So far we've accounted for 68% of our data. Within 2 standard deviations of the data, we know that that accounts for about 95% of the data. So if we do 95 minus 68, that means we've still got another 27% of the data that would fall in between 1 and 2 standard deviations. Half of it's to the left and half of it's to the right. So 27 divided by 2 is 13.5. So that means between 1 standard deviation and 2 standard deviations on the right, we'll have 13.5% of the data. And also between -1 standard deviation and -2 standard deviations, that's also going to contain 13.5% of the data. If we go out 1 more standard deviation to the 3rd standard deviation, we know that about 99.7% of the data falls within 3 standard deviations of the mean. We've already accounted for the middle 95%. So if we do 99.7 minus 95, we get 4.7% of the data that's still in between the 2nd and 3rd standard deviations on both sides. Since this is symmetric, that means half is on both sides. So if I do 4.7 divided by 2, we get 2.35. So that means about 2.35% of the data is between 2 and 3 standard deviations, both on the positive and the negative side. And lastly, so far we've accounted for the middle 99.7% of the data. So if we subtract that from 100, there's only 0.3% left, half on the left, half on the right. So if we do 0.3 divided by 2, we get 0.15% of the data would be more than 3%, more than 3 standard deviations above the mean, and only 0.15% of the data would be more than 3 standard deviations below the mean. So whenever I do any question asking me to estimate a certain amount within this normal curve, I start by drawing this picture every single time. Then I go back and look at the question. So first we're being asked to find the percentage of the batting scores that would be above 0.392. First we're going to find 0.329 on our bell curve, and then we're going to shade in the part of our curve that is from that much and up. So that was at the 2 standard deviations mark. Now that was 2.35% of the data that was between 2 and 3 standard deviations, and another 0.15% of the data that's above 3 standard deviations. So when we add those together, we find that 2.5% of the batting averages in the major leagues that year were above 0.329. Next, if we want to find the percentage of the batting averages that are between 0.227 and 0.295, we have to find those values in our normal curve. Here is our 0.227 and here is our 0.295. So we're trying to shade all these values in between here and here. From the 0.227 to the 0.261, that was 34% of the data. From the 0.261 to the 0.295, that was another 34% of the data. So there's 2 little sections that I shaded in our diagram. That gives us approximately 68% of the data, or 68% of the batting averages would be between 0.227 and 0.295 for that 2009 baseball season.